All right, so now the stage is set, we can talk about where the water in the ocean comes from. So there's two main ideas about where our oceans could have originated from, and we'll talk about both hypotheses. Then we'll look at the isotopes of oxygen and hydrogen to think about how those can be used to answer where and when this water arrived. So, we know our planet Earth as the ocean planet because almost 70% of its surface is covered in blue water. However, it's kind of humbling to realize that that's just this skin layer. And if you were to ball up all of the water in the oceans, you'd have something that would sort of fit over North America, be quite tall, but is a lot less than the solid, bulk rocky Earth. Our oceans are almost all the water on our planet. There's only 2.5% of the water on Earth can be qualified as fresh water, and most of that is locked up in ice sheets in Greenland and Antarctica. So less than 1% is stuff that we would use to drink in lakes, in rivers, in groundwater, or in the atmosphere, or within living organisms, for instance. So one of the main reasons that Earth can maintain water is because its orbit falls within the habitable zone. This is a Goldilocks region in terms of distance to the sun, where it's not too hot or too cold. If Earth was a lot closer to the sun, for instance, around Mercury, all the water in our oceans would boil and form our atmosphere. If Earth is further away, like in Jupiter, all of the water would turn to ice and there would be no liquid water. So this is a pretty popular concept especially for looking at other solar systems further out into space and thinking, could they have water? Could they have the ingredients for life? But there's a bit of a problem here. But as we discussed earlier, this was not the conditions of the younger solar system. When Earth first formed, it was a collection of rocky planetesimals where where conditions were too hot to support liquid or frozen water. And that's why our planet is mostly rock and only a small amount of ocean. And then, after that, we have this last explosion of the Earth-Moon forming impact, which is violent enough to launch any original atmosphere that created with Earth, to launch that back out into space. And so when you see, representations of this early period of Earth, this is called the Haitian Period, because Hades is the Greek sort of mythological representation of the underworld. Things are pretty hellish. There's a lava ocean, and then there's this crust that forms, but there's still volcanoes breaking through everywhere. There's lightning everywhere. There's not much water on the ground. It would be hard to survive if you were sort of transported back in time to this period. So obviously we live in a much more habitable planet today, and this is in large part because of the arrival of a full ocean amount of water. So where did this actually come from? There's two hypotheses about the source of Earth's water. One main group of hypotheses is basically bombardment. Earth's water is from elsewhere in the solar system and arrived by comets or asteroids that had ice or water attached to them, hitting Earth and then donating their water as they collided with our planet. The other hypothesis is that Earth's water comes from within, is that it's part of our mantle and it's released through volcanic activity sort of gradually over time. So over the last several decades, the bombardment hypothesis is the most popular, and that's because we have good models for what could have hit Earth to give Earth's water. Comets, if you've ever seen one, they're pretty remarkable. They have these long tails. A big part of comets are frozen water ice, and the tail of these comets are actually the ice sort of being melted off by the heat of the sun. But overall, these are called dirty snowballs for a reason. There's a small amount of rock and lots of ice, and so if these were to hit Earth, they would be delivering water to Earth. So when we talked about the formation of the solar system, we sort of located most of the comets out here in this Oort cloud, or in this Kuiper belt beyond Pluto here. This is on the far on the other side of the frost zone, so that's where a lot of the water in the solar system has ended up. But even though their average position is pretty far away, they have these really irregular orbits, and that takes them much closer, these loops around the sun where they can bypass Earth and even collide with it. So this is a viable source of Earth's water. There's also this asteroid belt here between Mars and Jupiter where there's all of these rocks, but we think that the conditions of Earth were we think the conditions of this asteroid belt were probably too hot in the formation of the solar system for a lot of ice to be part of this material. So another support for the comet hypothesis comes from this idea of a late heavy bombardment. This idea is based on evidence from the moon, where all the largest craters on the moon have a similar date in terms of when we think they were formed. They're all around 3.8 to 3.9 billion years old. And we know the dates from this because these collisions ejected new meteorites of lunar origin that then are found on Earth today. So the thinking is that after the solar system cleared of planetesimals during the formation of the planets, there's a period of relative quiet that then this picked up again in this late heavy bombardment where asteroid and comet strikes increased again. One of the ideas for the triggers of this late heavy bombardment is a shift in Jupiter's orbit. Jupiter's orbit here on the schematic is shown in green here, followed by Saturn, Uranus, Neptune. And the idea is that this whole Kuiper belt of comets and asteroids, well beyond the frost line, these are water, rock, combos of space debris, that their position was perturbed by this series of events where Jupiter shifts its orbit, Saturn shifts its orbit, Uranus shifts its orbit, Neptune shifts its orbit, and all of a sudden, all of these icy particles out here are subject to weird gravitational forces that send them sort of careening to the inner solar system and colliding with the moon, colliding with the Earth, colliding with all of the different objects in the solar system. So this could be a big source of water because you're delivering you're delivering objects from the other side of the frost line into Earth. So how do we know if this is where Earth's water primarily came from? Well, we have this constraint on Earth's water based on the composition of its isotopes of hydrogen and oxygen. You'll remember hydrogen has two stable isotopes, H1 and H2, or deuterium. Most of the hydrogen is found as H1, as this just a proton and an electron, but a very small amount, about 1.5 molecules per 10,000, 1.5 atoms per 10,000, is found as deuterium, where there's a proton and a neutron. So in trying to figure out the origin of Earth's water, this deuterium to hydrogen ratio is a really crucial constraint because it can rule out certain sources. There's been a big rush to measure the deuterium to hydrogen ratio in different comets. This is a compilation of data that we have here. And overall, from these three different comets, Halley's Comet, the Hayek Comet, and the HB Comet, all of them seem to be enriched in deuterium relative to the Earth value here. So this means that comets themselves are an unlikely source of Earth's water. They would be delivering more deuterium than we have today on Earth. So the deuterium to hydrogen ratio in comets just doesn't match the ocean. It's really unlikely that the ocean came from mostly comets. What about this idea that that Earth's water came from within? Well, we can visit places like Kilauea in Hawaii, Iceland, other ocean islands where there's volcanic activity, and we can sample the volatile elements that are leaving this volcano. All of this comes from magma from the mantle, and so this is a good representation of what's currently stuck in the mantle that's currently outgassing even after 4.5 billion years. So if you sample a volcanic gas plume, what you'll find is there's a big component where it's water. It's mostly water. There's a lot of CO2 in volcanic gases. There's a lot of sulfur dioxide. That's what contributes to VOG, if you've experienced that here. There's some other things too, like hydrochloric acid. But the key thing here is there's water coming out of the mantle now that is adding to the water budget of our atmosphere. And over long periods of time, that could slowly fill the oceans. So this venting hypothesis, that there's water within the mantle that's coming out of volcanoes and adding to the atmosphere and the ocean, that's currently the favored hypothesis. This bombardment idea is really ruled out by comets, but there's a bit of a caveat here in that we haven't totally ruled out the possibility of asteroids. However, we can't really rule out asteroids entirely. We have a couple samples of asteroids that have fallen to Earth as meteorites, and we've been able to measure the deuterium to hydrogen ratio of those asteroids. So here's a review of sort of all of the deuterium to hydrogen ratios that we'd have to consider to solve this problem. We talked about how comets have around 3 per 10,000 deuterium to hydrogen, which is close to double the ocean value. So that's why we don't think comets are a viable source. Earth's mantle has a deuterium to hydrogen ratio that's just a bit less than the ocean's. So that's around 1.46 to 1.47. So if you add a little bit of comet water, you can recreate the composition of Earth's oceans. However, there are certain minerals that are stuck inside these asteroids that actually contain water as part of the crystal structure. This is an example. This is apatite, calcium phosphate. You can see here's one, here's two water groups that are sort of part of this mineral. So even though this isn't ice on the surface of these asteroids, a lot of asteroid collisions could keep supplying water. And the deuterium to hydrogen ratio so far has been measured to be 1.2 to 1.5. So this could still be where a lot of Earth's water comes from. And honestly, the true answer is we don't know. A lot of people like the idea that Earth's mantle is a source of the water because we can see volcanic activity happening today, but we can't rule asteroids out just yet. So the last question we can ask is, when did Earth's water arrive? And to do this, we need to go back to the Jack Hills, back to the zircons that are our best time capsule of the early Earth. What we'll do now is look at oxygen isotopes. Oxygen comes in two major isotopes. The major one is 16 oxygen, 99.76%. The other minor isotope is oxygen 18.2%. So these numbers here, overall, they're just averages. There are specific reactions that can happen that can change slightly the abundance of 16 oxygen versus 18 oxygen. Mostly what happens is oxygen 18 tends to prefer to be in phases where it's not moving around as much. So solid phases like ice or minerals, oxygen 16 likes to evaporate more. Basically, there are environmental processes that can lead to slight differences in oxygen isotopes. So if we're looking at the oxygen isotopic composition of these zircon time capsules, there's two possibilities here. One is that this ZrSiO4 mineral has oxygen that just reflects the composition of oxygen in the mantle. And the other possibility is that there's chemical reactions between water and rock that can change this ratio somewhat. So this is the compilation of the oxygen isotope composition of zircons that are found from 2.6 billion years ago all the way back to the formation of the Earth. Scientists are still hunting for more and more zircons to fill out this picture because it's a bit sparse, it's pretty unsatisfying. But this is still a really tantalizing clue that there might have been liquid water pretty early on in Earth's history. And that's because we have this very well-defined expectation for what the mantle zircon oxygen isotope should be. This is this value right here. This is the mantle oxygen 18 to oxygen 16 ratio. So if these zircons just formed from magma from the mantle, then they should have this exact oxygen isotope ratio. But what you can see here, especially among these really old samples here, you see these higher ratios. There's more 18 oxygen in these zircons. And that's been taken as limited but still very tantalizing evidence that there was water on Earth that was interacting with minerals and changing their oxygen isotope composition, and that is being reflected in these zircons. Is it proof? No. But it's probably the best evidence that we have from material that just doesn't survive longer than 4 billion years. So the best explanation of the elevated 18 oxygen in these really old zircons is that there was liquid water present that modifies the mantle signature and makes it a bit heavier. So overall, there's been kind of a shift between this idea of a really hellish early Earth where everything is bare, there's no water, to this idea that there could have been water pretty early on, and that this might have been much more hospitable to life and early microbial evolution than was often thought based on this sort of hellscape here. So to sum up, we can just go through the timeline of early Earth history. This black dotted line is basically showing the rate of extraterrestrial impacts. Obviously, when Earth forms, this rate is off the chart. There's so many meteors colliding. When the moon collides, a whole nother thing. But then things start to settle down. And as soon as things settle down, we have our evidence for liquid water. So this could be outgassing from the mantle. This could be some asteroid impacts that bring some water in. But it's probably before this late heavy bombardment period here where the extraterrestrial impacts come back up again. So there's also some very sketchy evidence for the earliest biosignatures based on really small inclusions within these zircon minerals. It's too sketchy to get into here, but please ask me if you're curious about them. This is some of the evidence for that life could have started pretty early on in Earth's history. And then after this late heavy bombardment period, there's evidence for microbial life and microbial fossils, and definitely evidence for liquid water. So this is suggesting that the early Earth might have been really ripe for life to evolve pretty quickly, which is a change, and it suggests that there might be other places in the solar system where similar evolution could happen. This is because we know that there's oceans on other parts of our solar system, such as the dwarf planet Ceres and the moons of Jupiter, such as Europa. These are areas where there are oceans. Some of them are fed by lots of volcanic activity at the surface of the moon. And so these are places that NASA is especially interested in exploring more to see if there's signs of life here. So when you're preparing for the exam, make sure you understand the two major hypotheses for where ocean's water came from and how we can distinguish them using things like hydrogen isotopes. And also make sure you understand some of the ideas behind the oxygen isotopes in zircon and how they don't rule out the fact that there could have been water, really early on in Earth history.